Hello, I would like to welcome you to the webinar Practical Signal Integrity for Improved EMI Control in PCB Design. And I'm glad that many people obviously do show interest in the topic of signal integrity and the correlation between signal integrity and the EMC behavior of printed circuit boards. Just to introduce myself, my name is Ralf Bruening. I'm working as a product manager and senior consultant in the area of high-speed design at the Zuken EMC Technology Center in Paderborn in Germany. I'm in EDA now since around about 30 years, dealing with any kinds of signal integrity issues, simulation issues, power integrity, IBIS modeling, and EMI. And I've structured the webinar in a way that I would like to give you a short motivation and introduction into the area of signal integrity. What is the problem? What is the root cause? And what's causing signals not to have an ideal shape, as we have seen, as we see that on the bottom of the slide, rather than we get somehow distorted signals, which are suffering reflections, which are suffering different kind of mismatch effects, which are suffering overshoots or undershoots and a certain amount of ringing. So I'd like to introduce into the terminology. I would like to give you some ideas how signal integrity can be addressed during PCB design. What are the key issues? How this can be applied in a PCB design flow on the example of the Zuken CA8000 system, where we do propose signal integrity to be performed in a concurrent manner. Means not generating any kind of smart netlist, any kind of smart input file for a simulator and then tossing that over the fence, rather than having access to signal integrity simulation in all of the phases of the PCB design flow. I would like to give you a short software demonstration on how we do address signal integrity during PCB design. Then I hope to have some time after the conclusion to answer you some questions which might occur. Before I start, I would probably correct a misperception probably some of the attendees may have. In Germany, we have since 200 years this picture, so-called Nuremberg funnel. That's from an old tale showing a funnel aimed to introduce knowledge into the head of children rather than sending them 5 or 6 years to school. If you believe that this 1-hour webinar is something like a signal integrity knowledge funnel, replacing any kind of signal integrity course, workshop, whatever, I have to say, this cannot be done by this 1-hour webinar. So we do have course offerings for teaching signal integrity between half a day and probably a week. There are other sources for education around. So this is for sure not aiming to make you a signal integrity expert within an hour. This webinar has a meaning to act as a teaser to make you interested how signal integrity can be addressed and how a software solution would look like to address signal integrity in a convenient manner during schematic design, during the placement, during the layout, or for addressing post-layout signal integrity issues. Before I start, I would like to give you a brief overview how we as Zuken do realize PCB design these days in the times where the old SD-RAMs are more or less fading away. We have double data rates now approaching in the 5th generation. We do have the situation that most of you are not designing just a PCB, you are designing a system comprised by several PCBs, rigid and flex in a combination, and then very likely you have high-speed issues, you have signal integrity issues beyond the border of a single PCB. Means very often you have to get information whether a PCI Express link or whether any signal leaving the board is arriving on the other board in a proper amount of quality. Furthermore, we have these days these super fast communication channels. So we have HDMI, we have USB, we have DisplayPort, PCI Express, SATA, just to name a few. So this increased data transmission is defining further requirements on the quality of the transmitted signal. For the power distribution systems, we observe that even applications where you don't expect it, like for instance the TV, are comprising due to the use of super complex ICs comprising up to a dozen or more different power distribution systems, causing additional design issues either. And last but not least, that's our observation very often still, the analysis tasks, and here in particular the signal integrity task, is very often performed isolated from the design process. Means you do have an isolated group which gets any kind of design data, and then based on the input files, based on the netlist, is performing any kind of analysis, and then passing the results, passing any kind of measures back to the design process. So you may ask yourself, is signal integrity analysis anything like we call it new kids in town? Not really. Signal integrity is in place since quite a while. Depending on how you far look back, you can look back more than 70 years, where we had these old telephone switch bars. Here an example from Western Digital from the 40s, where telephone calls have been connected by an operator. And very often we know these things only from black and white movies like Laurel and Hardy. So very often you have the situation that during a telephone call, you're able to listen another telephone conversation unintended. And that's a classical signal integrity issue, because that's crosstalk. That's a transmission, unintended transmission of energy. So that's in fact a kind of signal integrity problem taking place more than 70 years ago. These days, the whole thing is a kind of more complex issue, so we have a multidimensional problem. Assuming that we have a multi-board situation, we have a driver on one of the PCBs, we have the trace routing over the backplane or over the midplane, we have then the board-to-board connection, we have probably a cable in between, we have the routing on the daughter board, we have to model the driver and the receiver, and very likely if we have complex ICs, we have to model the parasitics of the package as well. So these days, signal integrity is a rather complex thing which has to be addressed. Signal integrity has a direct contribution to the EMI behavior, so signal integrity can be seen as a kind of inner level EMC of a board. So both signal integrity and power integrity do contribute to the overall EMC fingerprint or footprint of a printed circuit board. So designing for good signal integrity is the first start, the first attempt to mitigate, to manage PCB level EMI. And even more important these days is that you are able to design to the limits, to design to the limit of the form factor, to design to the limit of the cost allowed for your final product. And there, signal integrity analysis can help either. The whole thing did start in the 60s and the 70s of electronic design by the silicon vendors implementing or releasing design rules like allowed parallel lengths, allowed spacing, or what is the recommended impedance for any kind of interconnect. In the 90s and 2000 years, these rules got more complex. We had in Europe the CE sign emerging. We had software solutions becoming more smart. So we had the first field solvers showing up. We had the first signal integrity simulators showing up, allowing more or less decent simulations of, in these times, advanced interconnect structures like for Intel or AMC processors. However, these days, we have the situation that the advanced communication channels, the high data rates, so I do have customers where 56 gigabit per second is not exotic, but a commodity these days. We have the fast memories. All this together defines a very complex design universe. So designing PCB just based on rules of thumb may run out of fuel, may run out of steam. So here, working on a digital twin, working with a virtual prototyping environment, working with the capabilities to address all the high-speed issues in rules and constraints with analysis tools in the process will help. So we have these days a printed circuit board living somewhere in this Bermuda Triangle between signal integrity, EMI, EMC, and power integrity, and all these aspects are correlated to each other. All these aspects impact the overall performance of the printed circuit board. As I did mention, the whole thing did start many years ago with the design requirements, design documents released by the silicon vendors. So Intel, in the mid of the 90s, has released the so-called yellow books. So these have been design guidelines for the Pentium breed of CPUs. They have been issued under NDA, and they do comprise a bunch of different design rules, design requirements, where Intel states that's the way to make these ICs working on your printed circuit board. So you do have routing requirements, you do have trace widths, you do have spacing isolation rules, you do have layer stack rules. All this with the aim allowing you to implement the board. These days, these rules are that complicated that eye widths, eye opening, eye patterns are given as a design rule for you to implement a trace following that rule on the board. So you may then assume, okay, before entering this nightmare of simulation and dealing with all the rules, I take the reference design of the silicon vendor, more or less do a copycat of that, so implementing this reference design for my application. So the question is, does this work for modern sophisticated technology like fast memories or PCI Express? So my answer would be, it depends. So I recommend be very careful in just adopting the structure of a reference design. I've seen users doing a Gerber in of the routing pattern of a reference design and then just redraw, do repaint the routing structure and then implementing a DDI interface in that way. But keep in mind, the IC vendor is implementing the silicon in a completely different manner than you are doing that. So they have complete different cost constraints, form factor constraints, layer stack constraints. So they very likely use the silicon completely different than you are using the silicon. The boards are typically rather large. Instead of doing that, I do recommend design with signal integrity in mind and, of course, as well with power integrity in mind. Know where problem areas are, establish design rules addressing these problem areas and avoiding traps and pitfalls. So high-speed design, which is more or less one of the root causes for any kind of dealing with signal integrity. High-speed design is comprising what I define as a puzzle. And the first and probably the most important puzzle piece is dealing with the stack-up of the printed circuit board. Dealing with the stack-up is like dealing with the basement of your house if you are aiming to erect a new house. If you mess up with the basement, then sooner or later your house may collapse. Same with the stack-up in a printed circuit board. If you mess up with the stack-up, curing issues later on by fancy measurements, by squeezing the design to the limits, by adjusting trace widths or dielectric heights, may end up in a complete nightmare. So stack-up design is the most important puzzle piece of high-speed design. Stack-up design goes hand in hand with characteristic impedance. So the stack-up will define the impedance conditions of your traces. Furthermore, we have for most of the silicon vendors some kind of routing sequence rules. So they do define for the different applications the routing topology, which is a rule which is another or further puzzle piece. Depending on the application, termination may be necessary to eliminate any kind of impedance mismatch, to eliminate any kind of voltage divider which has been created. All this is defining a kind of rule set. So defining rules, which is these days defined as a constraint or as constraining, is the next puzzle piece. So do constraining throughout the process. Start with the constraining as early as possible, probably even before you start the schematic of the board. And the whole thing should be supported, and that's pretty important. In an idle situation, simulation should be a support process. Simulation should not just having the desire to detect errors, to do a kind of CSI, PCB kind of a thing to find out what has caused my printed circuit board to die. Simulation should be helping all the other stages, simulation for signal integrity and for power integrity. So let's go through the jungle of signal integrity problems. So what are the key effects which are addressed by simulation tools then? We do know reflection and ringing, which is a misshaping of a signal from the ideal rectangular square, any kind of discontinuity, by any kind of impact harming the transmission, slowing down the edges, or causing the edges to show any kind of ringing on the high or on the low stage. Very important, this is impacting the timing behavior of the signal as well. Crosstalk is an aspect where we have a transmission of energy from one trace to another, very likely caused by a parallel routing. This coupling of energy can happen on the same layer, but this coupling of energy very often happens as well from one layer to another layer, because you have very small dielectric materials within your layer stack. You speak about insertion loss and return loss if you would like to characterize the transmission behavior and frequency domain. So what is the transmission behavior over frequency to what frequency? What amount of energy can be transmitted from driver to receiver, and what amount of energy would be reflected during or over the interconnect? For high-speed applications like PCI Express, DDR, we do talk about things like inter-symbol interference, where I diagrams are the figure of merit. Going further, if you have so-called ZS channels, the bit error rate is another quality figure for describing the signal integrity. If we have the situation that some signals are in relation to other signals, like in the DDI interface, we have the relation between the strobe and the data and the address and the clock lines, then you have to look into many I diagrams of signals together, analyzing them, the signal and hold time behavior of these structures. To understand what's causing a signal not behaving that well, let's dive into the basics. Let's dive into waveguide theory. So let's look into an interconnect where we have a driver and a receiver. The interconnect is modeled in a way that the driver can be seen as a time-dependent voltage source. So we do have a rise time and a fall time describing the behavior of the driver. We have the receiver, which can be seen, very simplified, as a high impedance resistive load. And then we have the interconnect structure, which is a trace, which can be more or less simply modeled as an impedance. So it is a kind of a resistor. So we have this kind of artificial resistor, which is showing up if energy is traveling from driver to receiver. The energy, the voltage, is traveling along the trace. And then the signal is arriving at the receiver. And then we have the situation that part of the energy is reflecting back. So we do have then energy traveling back on the trace. This energy will harm a signal which is occurring from the next transition. So the next signal then will see a voltage impacting the shape of the signal. This is causing this kind of degradation. And if we look into the CMOS silicon structure of such an interconnect, we have on the driver side CMOS showing an output resistance during the switching state. This output resistance is somehow dynamic. So we do have an output resistance changing in the high transition from 0 to 1 between something like 5 to 30 ohms. While switching from high to low, we have an impedance of 5 to 15. Same as human beings. For us, it's more easy to going down a staircase rather than moving up. So we have this output resistance, and we have typical impedance values of the trace of the interconnect of 55 to 75 ohms. So what we have is we have the situation that these kind of artificial resistor will create a voltage divider. So when the signal is leaving the silicon and entering the trace, this is the first situation where we have a voltage divider where we see an initial reflection. So part of the energy is immediately bouncing back, misshaping the signal. And then we have at the receiver this high ohmic situation of the load. So this is more or less how typical digital interconnects do operate. The impedance itself is since many years defined by the silicon vendors. So here we have an example of an automotive microprocessor from NXP, where NXP is requesting the single-ended and the differential impedance to match with a certain amount of accuracy to the given values. Here 50 ohm single-ended and 100 ohm differential. So what happens if I ignore these impedance rules? I will get more reflections. So I may ask, okay, what can I do to get a proper figure of the impedances of my printed circuit board? So if you use Google to look for impedance figure, to methodologies to figure out what is this ratio of current versus voltage during the switching, because that's what impedance is, then you'll find dozens of different formulas which take the trace height, which take the height over the reference plane and the trace width as the key parameters, and then they will give you figures, quantities of the impedance. This can be quite okay, but you have to keep in mind this has a few drawbacks. First of all, this assumes the trace to be a rectangular figure. Due to the manufacturing process, due to the etching, traces will look like these misshaped trapezoids we see on the right of this slide. These formulas cannot take into account high frequency aspects like losses, skin effect. That's not something modeled in these formulas. And last but not least, these formulas typically assume a trace is more or less alone on a printed circuit board. So they model single-ended traces. They cannot model coupled structures well. I don't know any really good formulas addressing differential traces, neither any formula modeling crosstalk situations. So coupled traces cannot be modeled by formulas. Here, more sophisticated mathematical methods like field solvers have to come in place to address proper characteristic impedance figures. If you ignore these impedance rules from the silicon vendors, you may put your board on risk. So here we have an example of a low power DDR3 signal from a customer project, which we supported last year, where the impedance requirement of the silicon vendor here, Micron, has been route the trace with 50 ohms. The PCB layouter did route the trace with 60 ohms in close contact to the board manufacturer, taking into account they do have a tolerance of plus minus 20%. And then they produced a first board and recognized we do have some fault switching occurring. So we undertook investigations using our simulator, and we figured out the 60 ohm signal has this magenta kind of switching where we have a significant ringback. So we do have a logic change. We have a ringback underneath the logic threshold issuing timing errors. While with the help of simulation, we figured out that the best value for this trace routing pattern is to route it with an impedance of 42 ohms. That's the green waveform. So that kind of analysis, that kind of help can be done by using signal integrity throughout the PCB design. So let's look into the overall picture of high-speed design and where signal integrity is coming into place addressing these complex high-speed design issues. So we do have these days differential pairs to be everywhere. We do have differential clocks and the strobe signals for DDR. We do have differential interconnect structures for SATA, for HDMI, for DVI. So we do have all these weird routing rules. We do have the situation that in complex ICs, like an FPGA, where we're often based on the package, we do have different trace lengths from the ball to the die, which we have to adjust somewhere on the board. We do have rules like it's forbidden to cross a split in the underneath reference plane. We do have length adjustment or stub length rules. So this is defining a kind of very complex design universe comprising impedance control rules, comprising lengths and length relations. So we have skew within differential pairs, we have skew between different differential pairs. All the different lanes of the PCI Express links have certain skew requirements. DDI interfaces show different skew requirements. We do have topology rules. So what is the proper routing sequence? We do have rules like there has to be a discrete device like a resistor, or for PCI Express, we have AC caps request to be within the line of a differential pair. We do have skew requirements between different signals, like between the clock and the address and the data and the strobe lines of a DDI interface. We have to have within the design process capabilities to define all these rules, to do what's called constraining. We need constraining mechanisms like pin pairs. We have constraints for impedance between two pin pairs. We have constraints like the maximum amount of wires to be allowed between two pin pairs, or to be allowed within a whole differential pair. We do have to have capabilities to design against these rules and to get feedback during the design process, whether these rules are met or whether these rules are violated. What-if capabilities are beneficial to figure out what happens if I choose a different topologies. If I don't do a flyby daisy chain for my DDR4 interface, rather than doing that, I implement these DDR4 using a T branch topologies. What's happening if I neglect the recommendation to use terminations because my form factor is rather small and I cannot afford that amount of termination resistors on this tiny little board I'm implementing? And for supporting all that, the capability to address signal integrity and power integrity using analysis tools in a concurrent manner means having analysis on the right mouse button during the design process allows immediately to judge the electrical behavior, the electrical performance of the design. So that's the Zuken vision of high-speed design, addressing a flow where you have the constraint management tool, the constraint browser, to be the command cockpit for all high-speed activities, for driving the routing, but as well for driving analysis, for driving signal integrity and power integrity simulation. So there you can, even before starting the schematic, define the first rules. You can run pre-layout signal integrity simulations to figure out what is the maximum amount of net length based on Manhattan distance, because it has to fit on a decent form factor. During the schematic design, you can create more complex rules. You can create the routing sequence by creating so-called topology templates. These topology templates can be amended with rules, with a routing layer, with a target impedance, with length definitions between two pin pairs, with any kind of termination rules. And then by assigning such a topology template, which can be extracted from the routing as well, so you can reuse existing IP, by assigning such a topology template to a net, to groups of net, these nets automatically will inherit all these rules. So this allows a smart and fast constraining by hierarchies. And during the layout process, you always have the desire to figure out what is the impedance condition. What happens if I route a differential pair in a kind of coplanar situation, which will harm the impedance? Do I have to take any measure against that, or is my board capable to sustain that kind of impedance mismatch? What is my signal integrity behavior? Do I encounter crosstalk issue? Or how is my power integrity? So here concurrent analysis helps to improve the design quality. An important aspect is that signal integrity phenomena can be described in both, in time domain and in frequency domain. Both domains have advantages and disadvantages. You can, mathematically spoken, transform using a mathematical process from time domain into frequency domain using a fast Fourier transformation, and you can go the other way around. However, as you have these aspects described either in time domain or frequency domain, We have implemented a time domain simulator and a frequency domain simulator within our CAD tool to address these issues. So you can run a transient analysis or TDI analysis in time domain, or you can run a frequency domain analysis because you may have things like insertion loss issues in frequency domain, while frequency domain cannot handle the nonlinear behavior of the devices. So semiconductor behavior is described differently in or more difficult in frequency domain. So therefore you have the two solvers available. The key is to have access to the simulation tools as easy as possible. So what you can do is you can select a trace or a bundle of traces, a bus, within the CAD canvas, and then directly launch a transient simulation, directly launch a TDR simulation, or directly launch a frequency domain simulation. So you have direct access to all the simulation tools from the CAD process. I did mention the constraint browser. You have the same access to the simulation tools from here. On the group of nets which you have selected for the constraint process, you can directly run any kind of analysis. Or if you create what we call a sandbox situation and pass groups of nets to an electrical equivalent circuit to be created and passed into the so-called electrical editor for any kind of sandbox what-if analysis, you have more sophisticated analysis options than from this electrical editor. You can run a transient, you can run a parameter sweep, you can run an eye diagram simulation from here. So you have access to the signature simulators on a few mouse clicks, giving you then information on the voltage versus time, or if desired, current versus time behavior, and all the relevant measurements for overshoot, undershoot voltages, for timing like rise time, fall time, are performed automatically and are shown in this kind of virtual measurement equipment. If you think about simulation, very often I'm faced that users claiming this is complicated. This is a weird process. I have no clue about all the modeling, so I don't like to do simulation. I will build up a prototype because that's the way I'm working since 30 years, and that's probably faster rather than dealing with all this modeling. So simulation is a kind of modeling, yes, but this modeling is a shared task between the user, which has a partial responsibility, of course, and the CAD system. So a large fraction of the modeling is taking place automatically. So if we look into this equivalent circuit of a DDR signal, where we have a driver, where we have a receiver, where we have an interconnect comprised of two wires and comprised of two transmission lines and a terminator in between. And starting with the transmission lines, these transmission lines are characterized by impedance. This impedance is calculated automatically by a very accurate field solver, and then this field solver is providing impedance and delay figures. This field solver is providing as well the complex circuit, so the resistance, capacitance, inductance values, and the frequency dependency, which are then used as an input for the simulation process. The active components, they are modeled by information provided by the silicon vendors, typically in the form of so-called IBIS models. IBIS models are a modeling standard invented a couple of years ago by Intel. So these IBIS is an acronym for Input Output Buffer Information Specification. It's a way to describe the switching behavior of active silicon. You do have sometimes as well SPICE models provided by the silicon vendors, but then typically somehow encrypted, so then very likely you may need a decryption key. You can model as well complex package situation as being part of an IBIS model. Wires are modeled automatically. They are described as a complex lumped so-called P circuit that's taking place automatically in a very accurate manner. If you, for whatever reason, believe that's not accurate enough because you are running any kind of 56 gigabit ZS link, then you can model any kind of wire structure by a black box model comprising S parameters. Discretes are in the most simple manner just modeled by a value. If you like to model the parasitics of a resistor or of a capacitor, you can utilize the SPICE model, or you can utilize the black box S parameter set. Let's dive a little bit into the details of the models for components, this so-called IBIS standard. IBIS is in place now since 1993. At the moment, revision 7 is under ratification, and IBIS models are supported by all signal integrity simulation tools being in the market these days. IBIS is supported by, I would say, 98 to 99% of the silicon vendors for digital circuitry, of course. And the CR8000 simulation tool, the CR8000 simulation process, based on a simulation library, which is populated, which is fed by IBIS models, or as an alternative by SPICE models by the user. We do populate it with some basic models, and then it can be easily further enhanced. The simulation flow knows different hierarchies of libraries. So we do know a project library, we do know a site library for the whole site of your engineering department, and we do know the mechanism. If you have the situation that you have a company-wide master library, it can be replicated. You can download in a regular basis the content of this master library to have then one librarian being responsible for maintaining all the libraries, depending on the way how you're working, whether it's done in the design department or at the designer level, or whether it's done on a central level, that simulation models are maintained in a similar way, like schematic symbols or footprints. I typically phrase that it's never too early to look for IBIS models, so this should be done very early in the design process, and it's same thing, never too early to assign a reference, to assign a link to an IBIS model to a design. So in the Zuken design flow, you can already amend the schematic with information. What is the IBIS model responsible or to be used for simulating that circuit? So you can use an attribute high-speed model to create a link between the schematic and the content of the simulation library. Of course, you can later on change this setting. You can force the software to do a smart research. Do you find something for this micron component MT41K256 within the simulation library? Then it's matched automatically. Or you can force a model assignment interactively, like you have the situation, I do have an assigned model for this micron memory, but I would like to play around a second or third source. I would like to swap this micron memory against the memory from Samsung, Hynix, or IXSI. So you can then, in any stage of the process, force a model to be something else. Like here, we are changing the receiver model to be a different one from this micron to be anything else. So you have access either to the whole pool of available models, or you can dive into different components from different vendors and then just changing either a pin or changing the whole component. And I'm often confronted with the question, do I get models for all my digital components? It depends, of course. But these days, all major IC vendors do provide IBIS models for their components. The problem is, if you use Google to do research for your desired component, you may run into a dead end, because these days, many of the IC vendors do protect their IBIS models and their IBIS libraries behind their customer gates. So you have to create an account, you have to be an Intel, Altera, Micron customer to get access to that information. So if you don't find the model on the web, I recommend please contact your field application engineer. They very likely are able to help you. So you are not blocked, of course. And another important thing to measure, I did mention these different kind of simulation methodologies for frequency domain simulation and as well for time domain TDI analysis. You don't need IBIS models. So you can perform such simulations without having models for the active components assigned. You need models for a transient simulation, figuring out the real interconnect timing, to figure out whether setup and hold requirements are met or violated. Typically, you find these models at the IC vendor website or at the resource pool of the IC vendor. Otherwise, CA1000 does allow to create a simple model describing the switching, describing the clamping, describing the voltage levels. So you can do simulations without models. If you need models, typically you get them from the silicon vendors. And just to mention, by the way, a PI simulation does not need IBIS models either. So it can be performed without an IBIS component model. So what can signal integrity simulation can do for you? Here we have the situation of a DDI interface between an NXP processor and a Micron memory. We do have the write and the read cycle from the CPU. So we have the voltage waveforms at the CPU depicted in red and at the memory in green. And we do see on both situations, read and write, we do have significant reflections. Why is that? Where do we get these reflections from? That's quite easy to identify because we do have within the interconnect different reflection situations. We do have voltage dividers we do create because we have an impedance value of 69 ohms. We have an impedance value of 107, 108 ohms. So we're around about 50 ohm impedance mismatch and we have a wire in between. All these are reflection situations. And we can use the SI simulator to figure out what happens if I route this in a different manner, not having any of these reflections. So for the sake of demonstration, I have here removed the two wires and I have adjusted the impedance, getting rid of the impedance mismatch, but with the same routing length. And what we see is the reflection is gone. So the signal shape here for this DDR3 signal is much nicer, much cleaner. So this allows to identify root cause of signal misbehavior and at the end of timing issues. That's what's taking place. This is impacting the eye diagram as well. So on the left-hand side, we have the signal with the reflection. On the right-hand side, we have the cleaner signal. And obviously, it impacts the eye opening and the eye width. A TDR analysis allows to figure out whether you do have changes in the routing widths, creating reflections. So we do have then so-called impedance discontinuities. I've created on a board, for the sake of demonstration here, this small bubble of increasing the trace width by the factor 3. Increasing the trace width means I will reduce the impedance number. Making the trace wider narrows down the impedance. So I have here now created the situation in the real design, we had 43 ohm. This changed small stub has now 28 ohm. And the TDR analysis will exactly show that. So this is a fast and comprehensive manner by giving you the analysis results where you have these kind of impedance mismatches and voltage dividers. Here we see the result of a whole DDR4 address bus, two DDR memory devices, flyby technology, 400 megahertz, speed grade 1066. Such kind of analysis, here we zoom into that area, and what we see is the behavior of the driver in red, and we have the two memories, that's flyby. So the memories see the signal with a tight delay. And as well within the address bus, we do have a delay, a skew between the 16 bits of this address bus. Is this violating the IC vendor rules? It depends. You can get such kind of an analysis result within less than 2 minutes because our simulation process, our simulation tool is distributing the simulation for a certain amount of nets on all the different cores, and then collecting all the different results. So this process is performing a parallel simulation. If you have to do things like figuring out for JEDEC compliance, how is the crossing point of a differential pair behaving? Because there is this rule, this has to be more or less in the middle, or there is a tolerance allowed of X or Y. You can use the simulator and the measurement capabilities of the simulator whether this is complied or whether this is violated. So here we have the crossing point to be 95 millivolt out of phase. And I did mention in the beginning, you have this correlation between signal integrity and EMC. Here we have the situation that we have routed on a small demonstration board a DDR3 signal over a gap in the underneath reference plane. So this is creating one of the most happening EMC issues, because we are creating here a parasitic antenna. We are forcing the return current to have a wider path from the receiver going back to the driver, and current always will return to its sources. So we have these parasitic antenna creating more EMC noise. But this is impacting signal integrity as well, and vice versa, of course. So I'm interested here for a moment into the signal integrity aspects. So I've created this situation in the sandbox editor. So I created a model with and without the gap, with the cutout and without the cutout. So this is a rather fast switching 1.5 volt DDR3 buffer. And if we look into the simulation results, we see, okay, this looks rather close, to be honest. There are tiny little difference, but there is secure switching above the limit, so I can probably assume, so what? It doesn't harm my signal integrity. But this is a little bit too optimistic. So if we zoom into that area of the receivers, we do recognize there's a delay, there's a skew between the two signals with and without the cutout. So we have a delta in switching of 18 picoseconds. Okay, 18 picoseconds. What's 18 picoseconds? 18 picoseconds is, depending on the technology, beyond the limits which are given by the silicon vendors. For instance, here we have an excerpt of a datasheet from Xilinx, where Xilinx is requesting the skew, the delay within the DDR signals should be within a window of plus minus 10 picoseconds. And here you introduce, by routing over the gap, a skew of 18 picoseconds. You should know what you're doing and what the consequences are, and signal integrity simulation can help you in getting proper answers to all these questions throughout the design process. To conclude, in the slide presentation with fast status channels, where we have the situation that these high data rate transmission signals do have very tight bit error targets. So USB, for instance, has a bit error rate of 10 power minus 12. Means 1 bit of 10 power 12 bits is allowed to be faulty. Otherwise, the receiving side is creating an error response. And the transceiver silicon these days can be programmed. So we can program the energy which is given into the ZS channel. And on the receiver side, we have capabilities to reshape the edges. We know different techniques for so-called equalization. So here, simulation can help, can allow to predict the eye openings, and can allow to predict as well what is the impact of these tuning mechanisms within the silicon. And as we cannot put a measurement probe within the silicon, this is a situation where simulation very likely is unique to provide you, before building the prototype, early information on the electrical performance. And this allows you to figure out, is my channel complying to the required bit error rate? And is my channel operating at the performance I'm aiming it to operate? If I'm implementing PCI Express Gen 4, I don't like to have it only operating at PCI Express Gen 1 or Gen 2. So to recap, where are we these days with PCB design? As already mentioned, PCB design is getting more complex on a daily basis. This is the case for most, not for all, but for most application domains, regardless whether it's automotive, whether it's industrial engineering, whether it's IoT, or whether it's things like climate control or fridges. They all utilize these days fast memories. They all utilize any kind of sensors and actors, gaining information, then transmitting this information using ZS channels. So analysis is more or less a commodity these days, being part of the PCB design process. So you should have analysis tools on your fingertips for all of the different aspects, for signal integrity, power integrity, EMI, and thermal. So we are phrasing that as allowing concurrent analysis throughout the PCB design. The design problems will further increase. This is caused by different aspects like increasing of the board technology and of course increasing of the IC technology, depending on Moore's law, defining on a daily basis more and more transistors squeezed on the silicon. So the analysis tools must cope with that. PCB design must cope with that. We do have ZS channels with different encodings, creating these weird measurement pictures like on the right one for PAM4 link, operating at 56 gigabit per second. So a smooth integration of analysis tools is key for success. And what you have to keep in mind, 3D design is these days on every desk. We do have 3D analysis necessity as well. So the simulation process should support multiple situations as well. So this will now turn me to the demonstration part of this webinar, where I would like to use as demonstration vehicle a design comprising an area, FPGA, 2 DDR4 memories, and different PCI Express links. And I would like to show how impedance can be checked, how the field solver results can be used to figure out whether you do comply to impedance rules or not, how to figure out what is the crosstalk behavior to run a time domain and frequency domain simulation, and how to create in a fast manner an eye diagram for a DDR4 clock signal, how measurements can be performed, and what are the capabilities to do parametric studies like changing an IC or changing the on-die termination of an IC, and to conduct what-ifs in the sandbox editor. So this is my demonstration vehicle. This is this design comprising this area, FPGA, and comprising the DDR4 memory devices and having them 2 DDR4 interfaces, one to each of the memory ICs. And as I did mention, you do have, on the one hand, in a simple manner, the capability to choose one of these signals and then directly fire up any kind of analysis, or to generate a topology for this topology sandbox editor. So you can run a transient analysis, you can run a TDR, or you can run a frequency domain analysis. I did mention the central command cockpit for all these activities is the so-called constraint browser, which is a Zuken constraint management tool for CA8000, where I do have a tree view with all the signals, all the differential pairs, and all the buses of the board. It's allowing a comprehensive cross-bowl probing capabilities into the CAD tools. So if I move this a little bit to the left-hand side, whatever I select here is cross-selected there. And I can as well assess all the analysis tools from here. Like I would like to generate a transient result for that selected trace. Then the analysis is started. And when the analysis is finished, it's populating the digital oscilloscope and showing the result on the screen, including all the measurements which have been done automatically. I can zoom in and figure out what is the behavior at the receiver. And here on the right-hand side, I get all my key electrical figures for the voltages, for the timing behavior, rise time, fall time, setup, slew rate. So all the measurements are performed for you, for both driver, receiver. I can turn different waveforms on or off, like I don't want to see the voltages on the die, or I would like to see them on the die, because we do have a different behavior on the pin and on the die. So that's without and that's within the voltages at the die of the silicon. I can do this for a single net. I can do that for a group of nets, so selecting all those. and running my transient analysis. As I did mention, this is then creating a parallel simulation process. So it's automatically dispatched on the different cores of your computer. And then the different simulations, the results are collected when the simulation process is ready. As I did mention, you do have access to time domain and frequency domain. So you can run a frequency domain analysis, selecting one of the DDR addresses, and then you get insertion and return loss generated for that selected signal. These results can be exported as an S parameter set in the touchstone format to be used in other tools or to be used in measurement equipment to compare simulation against measurement. And I did mention I would like to show you how to deal with different aspects like impedance and crosstalk. So if you would like to generate the information, what is impedance behavior of these complete address bus, you can conduct the field solver to be used to generate a so-called pin pair route report, which is giving you on a report base information what is for all the selected nets the different impedance condition. This allows to do a review of the board routing structure and to figure out where do I have violations against my impedance rules. You get these impedance as well in a more depicted manner if you create this electrical equivalent circuit. So we've selected one of the tracks, and then I have here this equivalent circuit with the transmission lines with impedance figure. So this is a microstrip, the fan out. Then we have the wire here. That's then the automatically created wire model with the parasitics, the capacitance, resistance, inductance. This is then the strip line on the inner layer. Right mouse button, please edit the configuration, allows to launch the field solver to do parametric studies. Like I would like to increase the width. Increasing the width means reducing the impedance. So this is narrowing down the impedance from 51 ohm to 38 ohm. So this is giving you information on the impedance figures as well. And you can create a similar report as well for figuring out what's happening crosstalk-wise, for instance, in this DDR4 address bus. So I can create from within the constraint browser a so-called crosstalk estimation report. So this is doing a fast crosstalk analysis and collecting all the different crosstalk figures. So doing a summing up of the forward and backward crosstalk and telling you what is creating here this crosstalk situation. You can use cross highlight to figuring out, I do have a crosstalk situation here of 860 millivolt. This is creating by these traces here routed somewhere in parallel. Here 2D is probably giving me a better insight in what's going on. And this allows you to determine where are your crosstalk hotspots on the board. And if you're interested then into the real figures of your crosstalk, you can pass this into the simulator and run a transient simulation on that crosstalk to get the real waveform and to figure out, okay, I do have an overall summing of 280 millivolt in that situation, but this is somehow distributed across the switching. So I would like to see the transient waveform to figure out I have to do any kind of countermeasure in separating the traces further or doing a termination to clean some of the signals, or I can tolerate that amount of crosstalk. So at the moment, it is conducting this crosstalk simulation, as we see here, on that selected core. And as soon as that crosstalk simulation is finished, which is more complex than an atomic transient for a single selected signal, so therefore it takes a little bit longer, but it's still a very fast transient simulation, I believe. So at the end of that crosstalk simulation, you will get the transient waveform of that crosstalk figure. Okay, simulation has concluded to its end. Then we get the simulation result over here. And if we zoom into the area, we have the aggressor lines. And on the bottom here, we have the victim lines showing the crosstalk aspect, which we can then measure to get the figures of the peak-to-peak crosstalk, which is here something 97. Peak-to-peak means 180. And then you can take the decision, okay, you can leave it as it is, or you have to do any kind of countermeasure. If you would like to see how different groups of signals are switching in relation to each other, so here I do have an address line and the differential clock for this DDR4. I run a transient of these both signals, which allows me to estimate it, what is the setup and hold behavior of these two signals, how they are switching in relation to each other. So this is then the simulation result, the two signals driven by two different bit streams, two different patterns. You can define what is the pattern driving the simulation within the constraint browser. So you have selected this is a 100 nanosecond, 200 megahertz signal. If I would like to choose any other bit stream, you can pre-select a number of bit streams, or you can create your own bit streams, like I would like to run this at a speed grade of 800 megahertz. Then you change the bit pattern within the constraint browser. And here I do have now my simulation result for my differential clock. This is this one. I just look into the differential signal. I do have my common mode voltage and I do have my differential voltage. So you can do any kind of dedicated analysis, how signals are operating in relation to each other, take into account the true interconnect timing behavior on the driver and the receiver waveforms here. To conduct parametric studies, you can use the parametric editor in transferring a signal from the constraint browser into this equivalent circuit. I do have this routing pattern. I can run any kind of transient analysis, or I can modify the circuit. Like I can do copy and paste, creating the situation instead of one receiver, I now have two receivers. And I connect this, for instance, somewhere to this via or to this node here and rerun the analysis to figure out what would happen if I have, instead of one load, two memory devices as loads. So I will get a model assigned and get my result showing now, instead of one receiver, two receivers. So I have one receiver, two receiver, and I have a complete different waveform because I have more reflections on the driver side. I can add terminations, like I would like to add a terminator close to that and can rerun the analysis to figure out this is a good measure or this is a bad measure to cure my signal integrity misbehavior. I would like to throw this away. And the last topic I would like to show you is how you can create an eye diagram for the figure of merit for the interconnect behavior of a differential pair running a high bit rate. So I create from this differential clock input for the electrical editor. This is then a more complex kind of a structure because I have a couple of single-ended structures and I have a couple of differential transmission lines. So if we zoom in here, this is my driver IC. I have here the fan-out region where I have two microsubs uncoupled. I have here some uncoupled areas, and then I have a couple transmission lines. If I select the transmission lines, it shows me this is an embedded differential strip line. It shows me the key parameters. So that's the result of the field solver. So this is showing a characteristic impedance of 85 ohms. If I dive into the field solver for this differential strip line, I can do any kind of parametric studies like moving it around, seeing, okay, if I move them further apart, my differential impedance will increase. So that's what rule of thumbs will tell you as well. But you can use the field solver as well to do parametric studies. Like I would like to do a kind of parameter sweep. What happens if I change my spacing between probably 100, that's what your PCB manufacturer is telling you is the smallest figure he can achieve in a decent quality, and 250, and then run the tool to give you how the values will change for the differential impedance and for the even and odd mode single-ended impedance. So you can use this parameter sweep, or you can do a kind of tolerance analysis. What's happening with all the figures I'm getting from my PCB manufacturer? And probably I'm considering a second source having different tolerance windows, so I can play around with 5% for conductor width, 3% for conductor thickness, 2% for edge factor, but I'm getting for the dielectric thickness here, let's say 25%, just for the sake of demonstration. This is giving me an impedance window for my differential impedance between 85 and 105 ohms. So that's 20 ohms just by the manufacturing tolerances of your PCB manufacturing house. So you can do all these kind of studies in running, adopting the field solver results. You can pass the results, impedance figures, then into that topology, and then use the simulator to figure out what is the impact on the electrical performance of these changed impedance behavior. And if you would like to get an eye diagram, you select these eye diagram analysis icon here on the top. You define what is the bit stream this should operate at. And I've created a 200 megahertz complicated bit stream to generate an eye. Not too complicated because an eye diagram then is running multiple simulation and is using a convolution to create the eye. So then this eye diagram simulation process is starting. As I did mention, it's collecting all the different waveforms, the rising and the falling edge, convoluting them and creating an eye. By that, doing all the different variations, including different jitter aspects. And this is then creating you the eye diagram result of the selected signal. And this is the result where you can toggle between driver and receiver. The result is showing you by the different color the bit probability. If you don't like to see this bit probability, you can turn a different mode. So this is driver and receiver. And you can use masks, which you can create by using the embedded mask editor. I've pre-created a mask for DDR differential clock. So you can create eye mask to compare The resulting I, that's for the driver. Here I have a violation against the mask, but I don't mind on the driver behavior that much. For me, the key and the compliance requirement for Micron or Samsung is defined by the receiver behavior, so I can compare my receiver behavior against the given I mask. And as I did mention during the presentation, that you have the possibility to change in any of the stages the models, which have in this case been pre-selected. I would like to play around here with the situation. This is a Micron memory device. I would like to change this, for instance, again, something delivered by Hynix or by ISSI. If I do this, select the component, confirm with OK, I can run the analysis with a different device. I can do similar operations. No, I don't want to keep this change. Similar operations from within the constraint browser, which is the cockpit for all the analysis process. So I can do here, I would like to change that device. Instead of being this Micron, you should be this Hynix device, you should be something else. You can do this on both ends, driver receiver side. You can drive the simulation here from the constraint browser. You can define which should drive the simulation, so which should be the so-called driver for doing an analysis of read and write cycles by determining this within the constraint browser. And then you can run the transient analysis in a convenient manner, giving you an analysis within a minute or less. The simulation process is ultra super fast. And that was what I had in mind to show you in the demonstration. And I would like to come to the conclusion of my presentation. So what I do identify as takeaways of the webinar is that signal-integrity analysis these days is a kind of commodity for at least digital high-speed designs. So the use of simulation tools can help you to validate the design and to take more or less solid decisions based on solid information. They can be pretty accurate. And even further, with the evolving of IC technology, we have the 5th generation of DDR knocking to the door. We have emerging board technologies. I see embedded silicon. I do see, even in automotive these days, embedded components and embedded boards. So the use and access to proper simulation tools can be a go, no-go situation, can decide to make or to buy parts of your electronic devices, and can allow you to be part of the competitive edge depending on what industry you're operating in. CA 8000 offers embedded analysis tools, so you have these analysis tools available within a single or a few mouse clicks. You can generate topologies, you can run transient analysis, you can run frequency domain analysis. In the same manner, you can run a power integrity analysis, you can run EMC checks. If these tools do not fulfill your desire because you have to model any kind of interference to an enclosure, then there are interfaces to third-party full-wave EMC tools, like from Keysight with ADS, like from ANSYS, which is HFSS, or like National Instruments, or CST with Microwave Studio. The key for success in using any kind of analysis tools is you have to know what is the modeling approach, what is the scope, and what are the limits to use the right tools for the right task. So what's next? What's next in EDA? What's next in automation? What's next in simulation? Everyone is speaking these days about AI, so do us. So we are considering to use AI methodologies, AI algorithms for the design of printed circuit boards, but as well to optimize patterns, analysis results. So we think about optimizing equalization patterns or decoupling schemes using AI algorithms. So that's probably what the future will bring, but that's in a pretty early R&D stage at the moment. And I would like to conclude with a further slide just depicting what Zuken is offering, because most of you very likely will see us just as a software provider. But we are more than just delivering software. We are aiming to help you to find high-speed problems before these problems find you. So we are delivering a very detailed training and education program for any kind of high-speed EMC signal integrity and power integrity issues. So they can least between half a day and a week. We do have dedicated courses for dedicated audience. We do even have a course introducing into AMC SIPI for department leaders, team leaders, managers, just to get a feeling or to create a feeling at the management level why this topic is getting more and more of importance and should be addressed within the ECAT flow. We are offering custom workshops. So we are taking designs from the customers and then doing dedicated trainings, dedicating workshops to do analyze together, to do hands-on, to do what we call a kind of co-piloting, flying the plane together with different aspects in mind, with signal integrity or high speed or even EMC. And last but not least, we do operate as extended or remote workbenches. We do offer design reviews for signal integrity, PI, EMC. We do use different simulation tools. We use our own tools and we use by permission third-party tools, like for instance for signal integrity. If we only have an HDevice model, which is encrypted and can only be decrypted by HDevice, we can use HDevice for SI simulation. We do help in optimizing designs. We do help in constraining. We do complex eye diagram analysis if the customer would like to have those. And last but not least, we do help our customers in maintaining their simulation library. So we do support in qualifying IBIS models, creating the proper model setting, for instance, for modeling slew rate or on-die termination settings. And I would like to put your attention to a workshop we are conducting on the 14th of March, taking place in Munich or in our Halberg-Moos office close to Munich, close to the Munich airport. It's called the Zuken Signal Integrity Experience Day. As this is the first of these events, this is free of charge, but the places are limited. So if this is of interest for you, use the link shown on this page or as well shown on our webpage to register as early as possible to this one-day seminar, which is a kind of hands-on using CA8000, using the SI simulator of CA8000. And it is divided in around about 25-30% a kind of introductional theory. And our aim is to have 75% real hands-on exercises, lessons to use our SI tools to solve real-life SI problems. And this brings me to the end of my presentation. For those of you who would like to dive into the details of high-speed design of signal integrity a little bit more, I would like to quote Eric Bogerton here: as board speeds go up, luck goes down. So that's a kind of real-life experience. And he is providing with number 2, one of the best books I know, which is now available in the 3rd edition, Signal and Power Integrity Simplified. This is probably the best start you can get. Number 1, Howard Johnson, Martin Graham, High-Speed Digital Design, a Handbook of Black Magic. This is more or less a reference guide. This is more or less a Bible, if I would like to say it that way, of high-speed design. Then the others are pretty good books either. Number 6 is, for my personal point of knowledge, the only good German one, which is available introducing into signal integrity. All of them are good references for getting started with signal integrity. So I would like to thank you for attending the webinar. And I would like to close with another phrase which I've seen at the wall in a customer side situation in a CAD department, where this department is supervising both simulation and measurement, stating no one believes in simulation except the guy doing the simulation. Everyone believes in measurement except the guy doing the measurement. So I would like you to think about that. Again, thanks for attending the webinar. If there are any questions which you may have, please feel free to contact me directly or to contact your local Zuken contact. And we would be happy to answer your questions and get in touch with you if you're interested to go into the details of concurrent signal integrity within the Zuken PCB design flow. Thank you very much.